Hi, and welcome to this talk. My name is Behrouz, and I'm going to present our paper, Materialization and Reuse Optimizations for Production Data Science Pipelines. This is a collaboration between several researchers from Hasso-Plattner Institute, German Research Center for AI, and Technical University of Berlin. Let's start with defining what are machine learning pipelines. To design ML solutions, data scientists start by finding and then processing the data in several steps, from simple analysis and pre-processing to feature engineering, selecting and tuning the model, and finally evaluating these models. After the evaluation, they may go back a step to further tune the model or perform different types of feature engineering, data analysis, or finding new data altogether. The final result, however, is a chain of components and operators for data analysis, feature engineering, and model training, which we refer to as a machine learning pipeline. This pipeline is then used for answering prediction queries. Typically, one pipeline may not suffice. Several data scientists or the same data scientists design different pipelines with different components. This is common in A/B testing for comparing the predictions of different pipelines, ensemble learning for combining the prediction of multiple pipelines, and continuous integration and delivery for seamless deployment of new pipelines. To fully take advantage of these pipelines, we put them in a deployment environment that enables us to scale and support any number of requests. In such environments, new training data continuously arrives and is stored in a storage unit. As time goes by, the quality of our model may degrade. Therefore, we periodically retrain the pipelines to ensure they stay up to date. The periodical retraining, as well as any similarities between the pipeline components, can result in redundant data processing and model training. And our goal is to eliminate such redundancies. Let's start with a concrete example. Suppose we have the following three pipelines. To ensure the pipelines stay up to date, every pipeline is accompanied by a training schedule. P1 is retrained every day on the last 30 days. P2 is retrained every day on the last 10 days. And P3 is retrained every 5 days on the last 10 days. If we look at the first 100 days after the deployment, we're in this scenario. P1 is executed on the last 30 days of data. Then we wait for a day. And then again, we re-execute it on the last 30 days. P2 is executed on the last 10 days. We wait for a day and execute it again on the last 10 days. And similarly, P3 is executed in the last 10 days, but we wait for 5 days between every consecutive execution. Now, there are 4 optimization opportunities that we can exploit. First, we can reuse the generated features of overlapping intervals. For example, for P1, every execution has a 29-day overlap with the previous execution. So instead of executing it on the entire interval, we reuse the 29-day interval and only compute the features of the last day. Second, some of the components have internal statistics, such as scale and variance thresholding. Similar to the feature reuse, we can reuse the statistics of such components and only compute the statistics for the new data. Third, these pipelines generate machine learning models that we can reuse to warm start future training operations. And lastly, the pipelines may share common prefixes. For example, P1 and P2 have the same first 2 components, or all 3 pipelines have the same first component. So instead of executing the pipelines one by one, we can share the execution of the similar parts. There are also several challenges that we should address. First, the generated artifacts are heterogeneous. For example, components such as polynomial feature generator and normalize generate what we call feature artifacts, which are essentially rows of data. Components such as scale and variance threshold also generate features. However, as described earlier, they also generate internal statistics that are quite different from features. The pipelines also generate machine learning models that are stored and used differently from statistics and features. Second challenge, the size and the number of the generated artifacts can become quite large. So we cannot simply store everything, and we have to come up with a solution to materialize only a subset of the generated artifacts. Third, depending on what artifacts are materialized, there are different ways of executing these pipelines. And we need to find the execution plan with a small overhead. And lastly, we are in an environment where data continuously arrives. Therefore, the distribution of the data may change. Reusing data blindly in the presence of a distribution change may lead to wrong results, and we should account for that as well. In the rest of this talk, I will be focusing on challenge 1 and 2, and I invite you to check out our paper for more details on the rest of our proposed solutions. To address the heterogeneity challenge, we need a unified representation of the artifacts. One particular challenge is that some components have internal statistics, such as scale here. Many machine learning libraries and toolkits represent such components with a fit and a transform operator, where fit computes the internal statistics and transform performs the actual data transformation. So the first step for us is to decompose these components into the two operators and transform our pipeline into a DAG, a directed acyclic graph. For example, our scale component now has a scale F, which represents the fit operator, and a scale T, which represents the transform operator. Every execution of the pipelines occur over an interval of data. For example, for P1, every execution occurs over a 30-day interval. So every operator generates artifacts over the 30-day interval. In order to design proper materialization and reuse algorithms, we not only need to consider the dependency of the operators, but we need to consider the intervals as well. Therefore, we propose a representation called the interval DAG, where every operator of the DAG also encodes the interval as well. Using this representation, we can implement our algorithm as I'm going to describe next. Now, given our representation of machine learning pipelines, we can define the materialization problem as the following. Given a storage budget, we would like to materialize a subset of the artifacts in order to minimize the execution cost of all the scheduled pipelines. There are several problems that we should tackle. First, the materialization problem is NP hard. In fact, a simpler version of it, where it only deals with batch datasets, is shown to be NP hard. Second, our solution must accommodate large number of pipelines. And lastly, artifacts are defined over intervals. This is problematic because it is possible that for an artifact, it is more beneficial to only materialize a subset of the artifact. Therefore, we should also consider the subintervals when deciding what to materialize. The overall solution that we propose is the following. First, we combine the interval DAG of all the scheduled pipelines. Then we compute a benefit score for every vertex in this combined DAG. We utilize our earlier work for computing the materialization benefit. And lastly, we materialize the vertex with the largest score. Let's take a look at a concrete example. Suppose we have P1 and P2 and their interval DAG representations. In our materialization algorithm, we start with the interval DAG with the smallest interval. In this case, that is P2. The goal is to combine the interval DAGs into what we call the materialization DAG. We start by adding the vertices one by one to the materialization DAG. Since the materialization DAG is empty for P2, we add all of its vertices to the materialization DAG. Next, we move to P1. When adding this vertex to the materialization DAG, the subinterval 0 to 10 already exists. Therefore, we split the vertex into two parts. The first interval, 0 to 10, is aligned with the existing vertex, and we just update the vertex information so we know it belongs to both P1 and P2. For the remaining subinterval, 10 to 30, we create a new vertex and add it to the materialization DAG. We do the same for scale F and scale T. Since the subinterval 0 to 10 already exists, we just split them into two subintervals. For normalize, the vertex does not exist in the materialization DAG. So we must add new vertices. Since the parents are already split, we have to split the interval of normalize into two as well. Lastly, we add our ML model to the materialization DAG. Now that the materialization DAG is constructed, we can use the following formula to compute the benefit of materialization. Let's go through the different components of the formula. V represents a vertex. Cost and size represent the generation cost and the storage cost of a vertex. The general idea is that we like to materialize artifacts that have a high generation cost but low storage cost. Next, we have the redundancy of a pipeline. We define the redundancy of a pipeline as the amount of redundant data processing that it generates. This is equal to the size of the interval divided by the slide. For example, for P1, the redundancy is 30 divided by 1 because we train it every day. This is equal to 30. This means that every data point is processed 30 times by P1. Again, the general idea is that we would like to materialize artifacts that result in high redundancy. For every vertex, we also have the set of pipelines it belongs to. For example, this vertex only belongs to P1, but this vertex belongs to both P1 and P2. Therefore, we should consider the redundancy of both pipelines for this vertex, which leads to a larger materialization benefit. This whole process is greedy. So once we materialize a vertex with the largest benefit, we should recompute the benefit of all other vertices and then select the vertex for materialization again. To evaluate our proposed algorithms, we used the New York taxi dataset and implemented 10 pipelines based on the top performing Kaggle competition. The goal of the competition was to design regression models for predicting the duration of a taxi ride. We used the dataset from the year 2015, which is roughly 24 gigabytes, and executing all the pipelines generates up to 2 terabytes of intermediate artifacts. We schedule all the pipelines to run monthly and use the last 6 months of the data in every execution. We compared our solution with TFX, which is a state-of-the-art machine learning deployment framework that materializes the last level features of the pipeline, but does not consider the materialization benefit of different artifacts. TFX also executes each pipeline separately. This is in contrast to our solution, where we combine all the pipelines and try to share computation when possible. We also compared with a naive baseline with no optimizations at all. In this experiment, we are reporting the cumulative runtime of all the 10 pipelines over the 12-month deployment period with different materialization budgets. When the budget is small, for example, 16 gigabytes, TFX performs as poorly as the baseline, since it does not select artifacts based on their materialization benefit. In contrast, in our solution, we try to materialize artifacts that have a large benefit. Furthermore, we share the computation of similar operators in the pipeline. We also see similar impact when the budget is large. Even though TFX manages to store nearly all the reusable artifacts when the budget is 128 gigabytes, its runtime is still larger than our solution. This is mainly because it executes every pipeline separately. This experiment shows that our proposed optimizations improve the runtime by 10 times when we compare with naive baselines and 3 times when we compare to the state of the art. In summary, we propose a solution for optimizing the execution of data science pipelines in production environments. We identified several challenges, and for each challenge, we proposed a solution. We designed an interval DAG representation to address the heterogeneity of the generated artifacts. We designed a materialization algorithm that assigns a benefit score to every artifact. In the paper, we also proposed a linear time algorithm for generating the execution plan, which incurs a negligible overhead. And lastly, to deal with distribution change, we introduced an approach for first detecting a change and then invalidating any materialized artifact that is affected by the distribution change. We also showed that our proposed optimization improves the execution time by up to an order of magnitude while incurring a negligible overhead. Thank you for your time.